Alright, so in this video, we are going to take an example of a projectile motion in which we are actually throwing the ball from an initial height. So problems like these come under the category of projectile from an initial height, and we will assume for the moment that we are throwing a ball which was already kept at a wall of height h sub 0 or h naught, and we want to see how the projectile follows, and we want to evaluate the same quantities that we evaluated for a normal projectile, which was the case when we were throwing the ball from the ground and it came back to the ground. In those cases, we were able to figure out the h max, which was this maximum height, the range, which was this, and the time of flight, which was the total time for which the ball was in the air. Now, when we dealt with questions like that, we were able to evaluate expressions for these quantities mentioned here. And I've expressed them here just for a quick revision. So h max was u square sine square theta by 2g, and r was u square g by sine of 2 theta, and time was 2u sine theta by g. Now remember, your theta was your initial angle at which the ball was thrown, and u was the total magnitude of velocity imparted initially. So with those parameters in mind, we were able to evaluate all these. But now we want to ask ourselves, what will happen to all these quantities in the appropriate definitions when the ball is initially thrown from a given height? Because this is normally the case. If you're holding a ball in your hand and you want to throw the ball somewhere, the ball is originally at a height. Now, you have to account for this initial height, which corresponds to almost the same height as wherever your hands are from in the vertical direction, and you have to keep this height in mind in order to really evaluate what happens to the trajectory of the ball. You cannot simply assume that the ball was at height of 0, all right? Otherwise, you'd go back into this situation. So we are going to go for a more deeper analysis, and we will be able to figure out the equations for all of these, all right? So let's begin. All right, so this is the problem at hand, and what we are going to do is we're going to solve the entire problem using the concept and the theory of vectors, all right? So if we want to describe a problem with the help of vectors, we must establish the vectors required. All right, so the first thing that we do is we say, all right, in order to use equations of v equals u plus at, or s equals ut plus half a t square, or u square, v square equals u square plus 2 the dot product of a and s. In order to use these equations, we must define what v is, s is, u is, a is, all right? So we have to define these 4 quantities. So let's begin. All right, so what we are going to do is we're going to say, all right, well, v is a vector at time t. V is the velocity vector of the ball at a given time t. Now we imagine that when we throw the ball, the time was set to 0, and we say when the ball reaches the final position that is on the ground, the time elapsed would be, say, capital T, and we will denote this as the time of flight. So at any point, at any time small t between 0 and capital T, say here where time was t seconds, at that point we can establish a velocity. So the velocity would be tangential to the projectile path, and we would call this vector as v of small t. So this velocity is a function of time. So we have taken that into account. Now, at that same time small t, we can also define another vector. That vector is the displacement vector, all right? So displacement vector, if you go back to the notes of what a displacement vector is, you would realize that it is the difference in the position vectors of the final with respect to the initial. So that means this is the final position, which is at t seconds, and the initial position was at 0 seconds. Then the line joining the initial to the final point is regarded as position vector at your time small t. All right, so this vector continuously changes, and so does the velocity vector. All right, but what do we know with absolute surety? Well, we do know the fact that at time capital T, the velocity vector would look something like this. All right, so this would be v of capital T, and the position vector would look something like this. All right, so this would be s of capital T. So remember one thing, small t is a variable here, all right? And we have to keep that in mind throughout. So we are going to use these properties in order to, first of all, use these equations of motions and also figure out what's happening. All right, so a key observation here, we see, well, S of capital T, which is this vector here, well, that would be the same as if this distance here, which is the range, if this distance here, the initial horizontal distance of the point and the final horizontal distance of the point at which the ball falls down, well, if that distance or displacement or difference in the horizontal positions is r, which we call the range in this motion, then if this is r and this height is h sub 0, then we can say with absolute surety that S of capital T would be, in our notation of vectors, we must write the horizontal component first. The horizontal component would be, well, this is the horizontal component. And if you see that this horizontal component is the same as the range, so we write r there. And if we are now to figure out the vertical component, which would be this, then we can see, well, that is the same as the height of the wall. However, since we're going down, then that must come with a negative sign. So this becomes negative h sub 0. So this is a key observation that we will utilize in the problem, in the problem that we are going to solve now. All right. So that's taken into account. Let us now write all the stuff that we know. So what is u vector? All right. U vector is the initial vector of velocity, and this can be regarded as u, which is the magnitude, cosine theta. So this becomes the x component, and u sine of theta, this becomes the y component. Remember, our coordinate system is always in this manner, where the x points here and the y points there. So the x is in the horizontal and the y in the vertical. This is taken as the origin. That is why all the vectors are defined with respect to the origin, and we are taking that into account every time. All right, so with a u established, we can now define what v of small t would be. Well, v of small t is a variable, and it will have two components: v of x, which is also a function of time, v of y, which is also a function of time. All right, so these, basically we are introducing two variables at this point. All right, now what about say acceleration? Well, acceleration is interesting because acceleration only points in the downward direction of g. All right, so what does that tell you? Well, acceleration, the total vector of acceleration has no x component, so that means x component is 0. But what about the y component? Well, the y component has to be, well, the magnitude should be g, but remember one thing, it's pointing in the negative, it's pointing in the negative y direction, so that would be negative g. All right, so that's the acceleration established. What about the displacement vector? Now, the displacement vector is a function of time, again, as we had already established, but we're talking about a general displacement vector, and that would be, again, s sub x of small t, s sub y of small t as well. So these are the vectors at hand. All right, now, so the interesting thing comes when we employ the three equations of motion. All right, so the first, let's employ the first equation of motion. So the first equation of motion says, let's get rid of this for the while. All right, so the first equation of motion clearly tells us that, all right, if you want to figure out what the final velocity is, well, the final velocity equals initial velocity plus a times t. All right, so we can simply write this in terms of this, this, and this, and that gives us, well, v of t is v sub x of t, and the y component is so. This should be equal to, well, u cosine theta, and then u sine of theta. I'm basically substituting u vector there, and we're adding that to a, which is 0 minus g, and we're multiplying it by t. So 0 times t becomes 0, and g times t becomes gt with the minus sign that was already there. Right, now we must add the two vectors, and if you add two vectors, their components get added, so that gives you u cosine theta, and the y component becomes u sine of theta minus g of small t. So this becomes your vector. Now, what is interesting is now you have equations and expressions for the components v sub x and v sub y. All right, so v sub x as a function of time becomes u cosine theta, and v sub y as a function of time becomes, well, u sine of theta minus gt. So that's interesting. What's that telling us? Well, that's telling us the same thing as what was happening when the height of the wall was 0, when we were throwing the ball from ground. What was that? Well, we knew that the horizontal component of velocity wasn't changing, so there is no change with time. So there's no change with time. So that's a small t right there. but the vertical component was gradually decreasing, and that is why you have a negative g times t there. And so much so that finally the vertical component of velocity actually becomes negative when t becomes much larger than u sine theta divided by g. So you can do the math and you'll see that that is when the quantity becomes negative. So there is a change with time, all right, but no change in time is seen in the horizontal component, and that is the essence which is still carried on in this problem. So that is interesting, all right, which should be the case because acceleration is only acting in the downward direction, not in the horizontal. So the vertical component is the only component of velocity which is affected. All right, I think I've stressed that quite a bit now. So with that established, what we can do is we can clearly make that substitution here, and we say, well, now that we know what v is as a function of time, what we can say is that, well, v vector would therefore be, as a function of time, would be u cosine theta, and then that would be u sine of theta minus gt. All right, so this is your final velocity vector at time t. Now we move on to step 2. All right, step 2 is basically when we want to try to express the velocity at the final time of capital T. All right, so what do we really know about final time of capital T? Well, the velocity vector at that time of capital T will look something like this, as drawn in pink, and we can either substitute capital T for this and get some sort of information, or we can use another equation, which is v square equals u square plus 2 times the dot product of a and s. All right, we can use this in order to figure out what happens at time capital T. All right, so let's try to do that. Well, what do we know? V square would be, well, Vx of capital T square plus Vy of capital T square. All right, that's this taken care of. What about u square? Well, u square is just the initial magnitude of velocity squared. So that would be, well, u squared. All right, so that can also be expressed as, well, u squared cosine square theta plus u square sine square theta. Now, this is the same as u squared. I'm just expressing it because I know the expression of the velocity, initial velocity vector. All right, so if I have to take the magnitude of that, I basically take the squares of both the components. And remember, that was the same thing I did here as well. I took the squares of both the components and I added them. So that is what I'm doing. Now, I go for the more interesting part, which is a dot s. Remember what a is, and remember what s is. Imagine this s is being evaluated at capital T time. So in that case, s becomes, well, we just figured that out, and that was the range and minus h sub 0. All right, at that point, acceleration was, well, acceleration will remain the same. It's independent of time. So this is the acceleration vector. Now, in order to evaluate the dot product, what we would do is a dot s at capital T would therefore be, well, r times 0, and the y, and we add, this is the dot product, we add the product of the y component. So that's minus h 0 and minus g. So we add that together, and we get, well, 0 times r is 0, h sub 0 h naught times g is hg, h naught g, and then the minus signs cancel, so you get g h sub 0. All right, so that is what the dot product is, and that is simply what we are going to write here. All right, so that is being taken care of. Let's get rid of that. And now what you realize is, well, okay, well, what can we do? Let's try to find an expression for this as a function of basically by substituting for everything else. So we know one thing, that if you look at the x component of velocity, well, the x component of velocity is independent of time. So it doesn't really matter if you figure out the x component of velocity at time t equal to small t seconds, or time t equal to capital T seconds. So this will always be the same as u cosine theta squared. All right, so we can simply write that in place of v sub x, and we're going to do exactly that. And what we get is u cosine theta. Well, we take the entire square of that plus v sub y at the capital T time, which is the final time, and we square that as well, equals u cosine theta square, and we must write the remaining part, which is this square, and we add 2h to gh sub 0, right? That was the dot product. Now what can we do? Well, it's evident. What we can do is we can subtract u cosine theta square from both the sides. That is equivalent to cancelling this out, and we get v sub y t square equals u square sine square theta plus 2g h naught. All right, and that is interesting. Now what we can do is, if you want to figure out what the final velocity vector would be as a function of this height, remember that we must take the root at both the sides. So if we take the root at both the sides, let me do that here, we get this and we get this. Now remember, this means that v sub y of capital T should be either plus or minus root of u sine theta whole square plus 2g h sub 0. All right, now why should be plus and minus? That is a property of taking roots. We always have to take into account both the signs. But which sign would hold in this case? Remember, in this question, what's really happening is you're giving the ball a push in the upward direction, but finally at capital T sign, the ball goes down and continues to go down. And when the ball continues to go down, we know that the vertical velocity is always going to be negative. All right, so if it's going to be negative, then we cannot take this sign of positive. We must only consider the negative sign. All right, so that is the expression of velocity, the y component of velocity, as of at the final time of capital T. All right, and we should also write that somewhere. All right, so with that in mind and with that clarified, what we can do is we can use the step 1 and step 2 of our approach. So step 1 was evaluating what this is, and we did that very correctly. We were able to evaluate the velocity at a regular or a variable time of small t. Now we know the velocity at a final time of capital T. What we can do is we can equate both of them given the time is same. So what we're going to do is we're going to say, well, v of at capital T should be the same as v of small t equated at or expressed at capital T time. Right, so this is what we're going to do. Now, at capital T time, this is what we know. So that would be, well, v sub x, remember, that is independent of time. So that would be u cosine theta. And what about the y component? Well, the y component would be negative root of u sine theta square plus 2gh sub 0. All right, and now we go back to step 1, which was this expression, and we basically substitute capital T for small t, and that gives us u cosine theta. Now, because there isn't a t coming here, we cannot do anything more than that. But in the second component, which is the y component, there is a t, and so we must write u sine of theta minus g of capital T. All right, so this is expressing it properly. So that is taken care of. Now, what do we get from this? Well, we see there's an equality that already holds, this equality. Both these components are the same, and they must be the same, right? Because this is the truth. The x component of velocity isn't changing, so there is nothing new we get from this. This is already implied. What about this? Well, this is interesting. Now what we can do is we can equate the y components as well. All right, because if two vectors are same, all their components are same. So if this has two components, both the components equate independently. So equating the y components, we get u sine of theta minus gt of capital T is negative root of u sine of theta square plus 2gh sub 0. All right, and what we can do with this is we can use this to express capital T. Now capital T therefore becomes, which is the total time of flight, therefore becomes, you do the math and you get u sine of theta plus the root of u sine of theta whole square plus 2g h sub 0 divided by g. So this is what you get as the total time of flight. So let us write that down somewhere for convenience. Now what we can do is we can figure out the other two quantities, the h max and the range. The h max is a bit simpler to understand, and that is because h max here would be the maximum height achieved by the ball, and that would be equivalent to basically evaluating this height. Now remember, this is the maximum height, which is h max, but the ball is initially thrown from a height of h sub 0, so we must basically add this h sub 0 to h max here in order to get the total height. But for generality, what really suffices is to evaluate this h sub max, and that is with respect to the original height from which it was thrown. Now in that case, it really doesn't matter if you're throwing it from a wall, if you're throwing it from Empire State Building, if you're throwing it from the ground, it really doesn't matter what height you're throwing it from, because this is relative to the initial position. So the equation for H max remains the same, and that is u square sine square theta by 2g, if I'm not mistaken. So that is indeed your total H max. Now, in this case, however, the total height would therefore be, well, u square sine square theta by 2g plus h sub 0. And that's it. That's the only addition to the problem that we've already solved. All right, so let's get rid of that for now and go on to a more interesting part, which is evaluating the range. All right, so we have to now evaluate the range, or capital R. So in order to evaluate capital R, we must employ this equation, which is S equals ut plus half a t square. All right, let's see how that works out. We are going to solve this equation at time t equals capital T. So that means that S, when at capital T time, would be, well, we know that vector is the range, and the y component would be minus h sub 0. All right, what about ut? Well, u would be u cosine theta and sine of theta, and we must multiply that by capital T, remember, because we're evaluating this at capital T time. And we must add t square, and we must multiply by the vector of acceleration, that's 0 comma minus g. All right, so add all the components here, and that gives you u cosine theta multiplied by capital T. And since here the x component is 0, that's the only component that remains. And the y component side, you get u sine of theta times capital G minus g by 2 capital T square. All right, so you get r equal r comma minus h sub 0 equals this vector. All right, so what can we do with this vector? Well, simple. It's really simple now. Now we must equate the x component with the x component and the y component with the y component. All right, so let's see what relations we get. So this is quite simple. What we get is r, or the range, is t times u cosine theta. And if I know what the expression for t is, which I do right there, then I can simply multiply by u cosine theta and get the entire equation. So that would be u cosine theta by g, and the g factor comes from here, and multiply that by u sine of theta plus the big root of u square sine square theta plus 2g h sub 0, and close the brackets. And this is my total range. This is my total. So this is my total range. This is my total time, and h max is still u square sine square theta by 2g. So there you have it. That's the entire problem solved. But wait a second. What do we get by equating the y components? Well, the y component of this expression gives you something which you already know, and it's not very hard to figure that out, because if you see, this relates h with capital T, and you also have u and theta involved. All right, so this is relating h sub 0 with capital T. So that means if I express this where t is the subject of the equation by equating both these quantities, then I would simply get something like this, because this is the only equation I know for t, capital T time, which is a function of u, theta, and h sub 0, which is right there. So that means solving this should give me this again. And you can check that because this is a quadratic equation, it will give you two roots, and the form is very similar, if you notice here, of the form of minus b plus minus root b square minus 4ac divided by 2a, something like that. All right, which is the equation for the roots of a quadratic equation, expression for the roots of the quadratic equation, right? So that is how you would go about doing a problem using vectors. So I hope this video made sense. I know it was a lengthy video, but I hope it made sense and it clarified most of your doubts. And stay tuned. All the best.